Okay, this is an example of how to design a double reinforced concrete beam. So we've got an example here. First, these two are the two equations we'll be using today. This is our example beam. It's a beam 400 millimeters deep, 300 millimeters wide. It's got some form of steel on the bottom. It's got some form of steel on the top. So we'll call it AST for area of steel and tension, ASC for area of steel and compression. The D is the depth to the bottom steel. The DSC is the depth to the steel and compression. All right? And we need to make that beam be able to carry 300 kilonewton meters. Okay, that's a bending moment. We're using 25 MPa concrete. And we're going to assume that we're using 32 mil bars, which are pretty hefty, fat bars. And we're going to use 30 mil cover. Just while you're thinking about bars, more smaller bars is generally a better idea. By the time you get to 32 bars, if it's more than sort of 5 or 6 meters long, one guy can't lift it up. So it makes your construction difficult. But we're using that today. All right. So first thing we need to do is to work out how much load can this beam take if it was singly reinforced. Then if that's less than 300, we're going to say, all right, how much steel for singly reinforced? Then how much extra steel do we have to add top and bottom to bring it up to 500? Okay? So the first step is to say, what's the most it can take as a singly reinforced beam? And we know, we're doing this, by the way, to Australian Standards AS 3600. And we're going to use the new code, which is the 2018 version. All right? Yeah, we're all excited. All right. So 2018 version, your maximum KU value is 0.36. Now KU, you probably recall, measures the depth to the neutral axis. So KU is a number that's between 0 and 1, and it talks about KUD is the depth of the neutral axis. So KU maximum is 0.36. So the neutral axis cannot be any lower than 36% of D. All right. So we'll do those numbers. So KU, which is 0.36. Oh yeah, let's get these out too. Alpha 2 is that's the amount of the rectangular stress block. You remember the stress block was like this instead of being, it was the real stress on the concrete is like that, and we approximate it to that. And that amount is alpha 2 times F dash C, and that dimension there is gamma times D. Okay? So our alpha 2 comes from clause 8.1.3, and there's a little formula for that. And the formula for alpha 2 and gamma are revised. They're different in the modern code than they are in the previous code. Okay? So alpha 2 is 0.85 minus 0.0015 F dash C, and that has to be less than 0.67. Sorry, it has to be more than 0.67. And F dash C is 25, so that equals 0.85 minus 0.0015 times 25, and that equals 0.8125. Okay? Alpha 2, we're going to need that soon, and we're going to need it a bit later as well. Gamma. Gamma is that distance that the rectangular stress block extends, and the formula for that is also revised, as in different in this modern code, and it's 0.97 minus 0.0025 times F dash C, the strength of the concrete, and that equals 0.97 minus 0.0025 times 25, which equals 0.9075. Okay? And so, yeah, we'll reference that. That's clause 8.1.31 and 8.1.32. So that's where you find those two equations in the code. All right. We know that now. AST is what we're actually trying to find. B is 300. All right. D is, yes, we have to work out D. Okay, so we've got 400 mil deep, and we've got a cover of 30 millimeters. So there's our 30 mil cover. So D equals 400 minus our 30 mil cover, and then we have to get to the centroid of the bar. So if the bar is like that, we have to get to the middle of the bar, so we're going to take the half of the diameter of the bar. Remember, it was N32 bar? So minus 16. 400 minus 30 minus 16 is 354 millimeters. Okay? Is that right?
Yeah.
Yeah, thanks. If someone just checks this and stops me making a mistake, that'd be awesome. While we're here, now I'll come back to that, don't worry. All right. So we've got that, I'm trying to find that. Area of the, the yield strength of the steel. Anyone? 500 megapascals. And the yield of the strength of the concrete? 25 MPa. All right. So that means that our Ku maximum, when that's a maximum, that's going to give our highest possible bending moment here. So our maximum Ku. What we're doing is we're trying to find out what's the maximum amount of steel. Okay? Then we'll put that into this equation. So our 0.36, just substituting into this equation now, equals 1 over alpha 2 0.8125 times gamma 0.9075 times area of steel, which we're trying to find, times divided by 300 times 354. There's our B, there's our D, times 500 over 25. Everyone okay with that? Okay. And if we work that out, we get, take the AST, the area of steel, leave the area of steel over there, put that up there, put that up there, put that down there, put that up there. We get that equals 0.36 over 1.356 times 20. That equals 20. And area of steel equals 1,409 square millimeters. Okay? Alright, so what we've worked out there is that when Ku is 0.36, the area of steel is 1,409 square millimeters. Alright? That is the area of steel that corresponds to the largest possible bending moment that this beam can carry as a singly reinforced beam. Alright? So now we just have to find out what that number is. We're going to substitute into this equation. So we've just found out that. Alright? So I'm going to rub off this. No, I'm not. I'm going to move the camera and keep going. Okay, so we've got that mu naught equation. And now the phi factor is another factor which has changed in the new code. And the phi used to be an easy 0.8 or 0.6, and now they've made it more complicated, and it relates to what your KUD is. Okay? So if you look up table 2.2.2, you find that for bending, phi equals 1.24 minus 13 Ku over 12. And we know Ku is 0.36, so that equals 1.24 minus 13 times 0.36 over 12, and that equals 0.85. Okay? Phi equals 0.85 for this problem. Alright, and that's got to be within a range, and I think that's the bottom of the range. So if your Ku is less than that, you get a better phi value than that. Alright, so now we know phi, back over here, we know the area of steel, we know the yield of steel, we know D, which is that value there, which is 354. 1 is 1, We know alpha 2 there. We know the area of steel. We know B, we know D, we know FSY, we know C. Okay, so we know all those numbers now. So now we can work out phi U naught, phi mu naught, which is this is the bending moment capacity of the singly reinforced beam that's this size. So that equals 0.85 times AST, which is 1,409, times FSY is 500, times D, 354, all multiplied by 1 minus 0.5 over 0.8125. That's the alpha 2 value. Times the area of steel, which is 1,409 over, over 300 times 354. Finally, times 500 over 25. And if you put all that into your calculator, and you do it the same as I did, which is probably right, you get 177.36889.4. And that, of course, is in Newton millimeters. So we divide that by a million to get kilonewton meters. Put a graph there. So we get 177.37 kilonewton meters. That's phi mu naught. All right. So what that's saying is, if our beam was a singly reinforced beam with the maximum amount of steel you're allowed to put in it, it will have a capacity of 177.37. Okay. But back over here, we need a capacity of 300. Therefore, this beam is not going to cut it as a singly reinforced beam. If the m star, that's the design moment, was less than 177, this problem is over. All right, but we've got to get to 300. So 300 minus 177.3, we are looking for an additional 122 kilonewton meters of capacity, right? And that capacity is going to come from adding top steel and adding more bottom steel as well. So that comes from having top steel, having bottom steel, and having a lever arm between them. Okay, that's the secondary beam we're talking about. Does everyone remember that? Smile, nod. Yeah. Okay. All right. So what we'll do first is we'll work out what the bottom steel is first, and then there's a few factors we have to apply to work out what the top steel is. Okay. If they were both fully yielded and isolated, they would be exactly the same amounts of area. Okay. But there's a few factors which mean this one's got to be larger. So, first thing is that lever arm. Okay, to get the lever arm, we come back to our beam here, and this bit over here. We need to find out that distance from there to the centroid. So that is, we'll call DSC equals, we've got 30 mil cover, plus half a bar, which is 32 mil, so 30 plus 16 equals 46 millimeters. Okay? That's 46 millimeters there. Therefore, our lever arm from there to there is 354 minus 46, which is 308. Okay? We have a lever arm between our top steel and our bottom steel of 308 millimeters. Okay. So our, I'm running out of board. Let's go over here. All right. So we have to get, to summarize, we have to get to 122 kilonewton meters using a bit of steel there, a bit of steel there, and a lever arm of 308. Okay? And so our phi m is going to equal the area of steel, sorry, phi there as well, the area times the area of steel times the yield strength, FSY. Okay? Times that 308. So if we take moments about there, area of steel times the yield times 308. So that's pretty easy to work out. So the area, sorry, we know M, it's the 122. We're trying to find AS, we know that and we know that. So I'll isolate it out and we'll say, this is useless. All right. Area of steel, oh yeah, phi is 0.85 still, is, sorry, I've done that wrong, that shouldn't be there. All right. Is 122, and we'll make that 122 million, because we're going back into our millimeter units now, divided by 0.85, divided by 500, divided by 308. And does anyone got that value? Yeah, here it is. And that should equal 936 square millimeters. Okay? So our additional area of steel in tension is 936 millimeters in addition to that 1409. So we've worked out the bottom steel that we're going to need in this beam. Now let's work out the top steel. Now the top steel, we need the same amount of force, but the top steel, A, may not have yielded, and B, has got some concrete in the way. So we've got to modify it a bit. So the first thing we need to work out is, has our steel yielded? And remember from triangles, we've got the strain diagram, which looks like that. There's the concrete strain diagram. There's our bottom steel there. There's our top steel. Okay? That distance is KUD, which is 0.36 times 354. All good so far? All right. Now the strain at the top. When you have concrete design, to get that rectangular block, this assumes that that strain at the top is 0.003. Okay? So that's a fixed value. We want to find the strain right there. And so we have a value there. We know that distance as well from there to there. Okay, so KUD is 0.36 times KUD is 0.36 times 354, which equals 127.4 millimeters. Okay, that distance there is 127.4. What's that distance? That is 127.4 minus that 46. So 127.4 minus 46 equals 81.4 millimeters. That's that distance there, 81.4 millimeters. Okay? So setting up like triangles, you know the ratio of that over that is the same as the ratio of that over that. Yeah? Okay. So let's work out the strain in the steel. So we know that 0.003 divided by 354 is the same as the strain in the steel divided by 81.4. Sorry. Talking about that distance, that's 127.4. That's better. Okay? That distance divided by that distance is the same as that distance divided by that distance. Okay? That's what we've got here. The strain over 127.4 is equal to the strain over 81.4. So take that across there. We work out that the strain in the steel is 0.00191. Now, to work out if that's yielded, we have to know the yield point of steel. The yield point of steel is 500 megapascals, and we know that the elasticity of steel is, anyone? I know you're thinking 200,000, right? Yeah, good. Yeah. Excellent, excellent. All right. So, stress, 500, sorry, what's the formula for this? Stress over strain. Stress over strain is the, yes, E equals the stress over the strain. Okay, so for 500, so that's 200,000. And 500 over the strain, take that over there, that across there, is 0.0025. Because 0.00191 is less than 0.0025, the steel has not yielded. So we have to work out what the stress is in the steel. Okay? So there's not enough stretch or compression in that part of the beam for that steel to yield. Okay? So the stress in that steel, so using the same equation, E equals stress over strain, then our stress is going to equal 0.00191 times 200,000, which equals 383 megapascals. So the stress in the top steel is going to be 383 megapascals, not 500. Because the stress in the top steel is less than the stress in the bottom steel, we need more of it in order to get a matching top and bottom force. Does that make sense? If we had 500 at the bottom and we had 100 at the top, we need 5 times the amount of steel at the top and the bottom. The ratio in this case is 383 to 500. All right. The last complicating factor is that steel is buried inside concrete. So if we take that full amount of stress of steel, then we have to compensate for it by giving it a little bit more concrete, which is crazy complicated, so we don't do that. What we do is we pretend that some of that steel is concrete, and we just use the remaining steel. So the concrete has got a stress of its own. Remember there was 25 MPa concrete? Okay. It's not quite 25 MPa, it's actually alpha 2 times 25 MPa is the stress in the concrete there. We take that off the 383, so let's work out that. I do have to delete something here, I think. No, I'll just work down. Alright, sorry this is all over the place. I didn't realize it would take this much. Alright. So where were we? We're 383. Yes, the stress in the concrete is alpha 2 times 25. So the stress in the concrete is 0.8125 times 25, which equals 20.3 MPa. So the stress in our steel in compression is going to equal 383 minus 20.3, which equals 363 MPa. Okay? That's the stress in our top steel now, 363 MPa. All right? We have to get enough steel in there to equal the force that the 936 millimeters of steel would equal. So, top steel. So we know that the area of steel, so I'll swap pens, this one's running out. The area of steel in tension times the yield strength of steel is going to be the force, is going to equal the area of steel in compression times whatever stress that steel is. Okay? And we know all of those numbers except that one. So can anyone see that? Sorry, I'll go up to, go over here. We're done with this now. All right, we're near the end. We're getting there. All right. So area of steel at top was 936 millimeters times 500 equals the area of steel in compression times 363. Take that 363 over to there, and we'll find that the area of steel in compression equals 1,238. Okay, so let's go back and revisit our beam then. So the area of steel in tension was 1,409 plus 36, and the area of steel in compression was 1,238 square millimeters. And that is 2,345. And that's the answer. If you want that beam to carry 300 kilonewton meters, you need 2,345 square millimeters of steel on the bottom and 1,238 square millimeters of steel on top. And then if you look up your red book, which has the bar areas in it, you'll find that 2 N28s will almost do that, and 4 N28s at the bottom will do that. Okay? Now remember at the beginning I said we assumed N32s? Yeah, it turns out I was wrong. It should have been N28s. So the effects on that are that the steel is a little bit lower, and so that lever arm is a little bit larger. So the beam is actually stronger than we've designed. So we can leave it at that. All happy? Was that easy? Yeah. Yeah. All right. If you have any questions, email me. All right. Or call me. Hashtag what? All right. I can't stop this. Come on, the mouse doesn't work. Nope. It keeps recording.